Okay, we have here today another integral from the MIT integration bee. This one here is from 2011, problem 21. We have the integral from 0 to 6 of the square root of 6x minus x squared dx. Okay, it looks like a fairly straightforward integral, but we have to do something with what's going on inside the square root here. I think we're going to need to do some algebra to manipulate this, maybe complete the square. So what I'm going to do is let's just break this out separately. And to start with, when I rewrite, I'm gonna actually factor a minus out because I kind of like having the x squared in front like this, maybe just a personal preference. And then to complete the square, I can just take half of the 6 here when I do this. So I can do this as, I can write it as x minus 3 squared. We'll put a bracket around it. And then you notice if we multiply that out, we get x squared minus 6x plus 9. Well, we can subtract off the 9 so that we're not changing it. And so then we'll just put the minus sign back in, and I can write this as 9 minus x minus 3 squared. And we'll take this, and I'm going to put this back into our square root and continue with the integral. Okay, at this point you may notice that this is actually ready for a trig substitution. I could do this, we could do a trig substitution for sine, but I think I'm actually going to do one more. I'm going to actually do this with 2 substitutions. I think I'll just make it a little more clear if I do a u substitution before trig substitution. So I'm going to call my u equal to x minus 3. I'll take a derivative, and we'll get du is going to be just the same as dx. So we'll update our bounds. If x equals 6, then our u value here is going to be 3. If x is 0, then u is going to be minus 3. Then updating our integral, we're just going to have 9 minus u squared du. And one other thing before I do a trig substitution, let's just notice that this here is an even function just because we have that squared term right there. And also we have symmetric bounds around the y-axis. That's going to allow me to change my bounds. What I can do is change this lower bound to a 0 and bring a 2 up front. That's just a property of even functions and symmetric bounds. So now I'm going to go ahead and do the trig substitution and just recognize that our 9 there, we can write that as 3 squared. So when I do this, I'm going to write my u as equal to, taking the 3 there, we'll write my u equal to 3 sine of t, take a derivative, du is going to be 3 cosine of t dt. And what I'm going to do is take this, and we're just going to get a value for t. So what I can do is divide both sides by 3, so we'll have u over 3 is sine t, but then I'll take an arc sine on both sides, and we can isolate t, so we'll have t is going to be the same as arc sine of u over 3. So now we'll go ahead with this substitution. For the upper bound, we plug a 3 in here, so we want arc sine of 3 over 3 or arc sine of 1. Well, that's just going to be pi over 2, and then we'll plug a 0 in, we want arc sine of 0. That's going to happen at 0. And then for this, we're going to have 9 minus u squared is going to be 9 sine squared of t, and then our du is going to be this 3 cosine t dt. So we'll take a 3 out here, a 3 out here, that's going to be 9. We bring it in front of the integral. 9 times 2 is going to give me 18 out front. Then in the radical, now that we factored out the 9, we're just going to have 1 minus sine squared t times cosine t dt. But 1 minus sine squared t, that's the same thing as cosine squared t. We're inside the radical, that's going to give you absolute value of cosine t. But because of our bounds, this is always going to be positive. So I'm just going to write this as cosine t. So multiplying these cosines together, we're just going to be integrating cosine squared of t. But then I can use the power reduction on this cosine squared of t. And I'll write it like this, half times 1 plus cosine of 2t. Now what I'm going to do is take this half outside the integral, multiply it times the 18. So we're going to have a 9 out front now. And then we're just going to have 1 plus cosine of 2t dt. So then I'll just integrate this. Integrating 1 is going to give me a t. Integrating cosine of 2t is going to give me sine of 2t over 2. And we just need to evaluate this from 0 to pi over 2. But it's getting crowded over here. I better clean up the board. Okay, now from here I just need to evaluate this thing to finish this off. And so first I'll just notice when we plug a 0 in, sine at 0 is going to be 0. So everything at 0 is going to be 0. Then I'll plug my pi over 2 in, so we're going to have 9, plugging pi over 2 for t. So then we're going to have 9 times pi over 2, and then we're going to have pi over 2 times 2 is going to be, we're going to have sine of pi over 2. Now sine of pi is 0, so this is going away. So we can just multiply this in, and so for our final solution, we're just going to have 9 pi over 2. Okay, again, so it was a pretty straightforward problem, but still a pretty good one. So we'll stop it there. Thanks everyone for watching today. Have a great day.